Hi, everybody. So this presentation is basically about what we've learned from the metadata performance testing at Xyratex. So the outline, first some brief overview of metadata performance testing, and then we'll talk about our testing methodologies. And then at the end, we'll talk about how we carry on our investigations when a metadata performance issue happens. Okay, overview. Lustre metadata performance was less well studied than data performance in the past. We see a lot of publications about data I/O throughputs published by different organizations or vendors. So for example, we see Blue Waters, the first one, reports passing the 1 terabytes per second throughput mark, and then DDN, Oak Ridge, and then Fujitsu all publish similar results. But on the other hand, there's not much publication about the metadata side. The reason is that Lustre is typically used for the batch mode intensive data processing, which doesn't require much from the metadata side. But now things are changing. We see more attentions on metadata performance lately. And the reason behind that, so the first one was also mentioned in some earlier presentations, is that certain type of HPC applications will generate a lot of temporary files and delete them when the job is done. So for those type of applications, they have some certain requirements on metadata performance. And then we see new application models. So like auditing software, they will periodically walk through the whole Lustre namespace to gathering the metadata from the file objects. And the same thing for backup and restore softwares. It will generate the inventories by traversing the Lustre namespace. And then yesterday we heard about HSM, and I'm sure that will also have similar, metadata operations. And then the last one is people are using Lustre as the backend storage for file sharings. They put an NFS SIFS gateway in front of Lustre. So in that type of file sharing applications, they're more in an interactive mode. So there are more metadata communications between client and servers. And the last one is that we see competitions from outside Lustres. We see people comparing Lustre with other distributed file systems like GPFS. Also, people comparing Lustre with other data storage solutions like clustered or scale-out NAS solutions. So all this requires us to have a thorough study on the metadata performance of Lustre, what Lustre can offer, and what's the limitations. Especially now, thanks to Intel, we have this new features, the SM scaling features for 2.3 and the DNE features in 2.4. Both will dramatically improve the metadata performance. So we want to know what we can get the most out of Lustre in terms of metadata performance. So next we'll talk about the methodologies we're using. The first thing is about benchmarking tools. So we use MD test most of the time. But there are two other benchmarking tools as part of Lustre distribution is MDS survey and MDS rate. MDS survey is like OBD filter survey. It will just run directly on the MDS node without any clients, without any network latencies. And then we see other organizations using their own benchmarking tools like MetaBench or Bunny++. And then spec SFS. So if you're using Lustre with NFS SIFS, and spec FS is like the standard benchmarking tools for NAS to measure NFS and SIFS performance. And then also some other homegrown tools. It's worth mentioning that there is a subgroup called metadata benchmarking group under the OpenFS benchmarking working group. They're working on compiling a list of benchmarking metadata benchmarking tools and do some evaluations on those tools. So you can go to OpenFS wiki to check it out. The next thing about methodology is hardware configurations. The first one is the backend storage. So for metadata performance, latency is more important than throughput. So you want to get a backend storage that can provide a high I/O per second. So in order to do that, you just add more disk, more spindle, give you more parallel operations. People are using either software RAID or hardware RAIDs, or you can use SSD to achieve that. And the next factor is the journal of the backend LDiskFS file system. So it seems like the bigger, faster journal will benefit file system operations that tend to generate a lot of random disk IOs, such as unlink operations. And the possible reason behind that is that journal updates tend to be like a sequential operations. So basically, the journal becomes effectively a caching device for all those random metadata disk IOs. And then the next factor is CPU and memory. You see the figure to the right shows the CPU utilizations and 3 disk utilizations. It's from the same MD test runs. And you see that the one below is the 3 disks. You see it's underutilized. Most of the time it's like 50%. But on the above figure, you saw the CPU was running most of the time on 100% load. So clearly, the CPU is a bottleneck of this certain this kind of hardware configurations. So you want to get more metadata performance, you have to have a more powerful CPU. And the last one is the networks. So before you run your specific metadata performance benchmarks, you want to make sure you have a healthy network. So the tools we're using is the LNSF test. And it runs in 2 modes, either pin mode or log mode. For measuring metadata performance, you want to use the pin mode to see how many RPCs per second you can get. So normally with the InfiniBand, you can see like hundreds, thousands of RPCs per second. If you see numbers below that, you have some problems with your networks. And the next thing of the methodology is MD-test specifics. MD-test has a bunch of parameters you can tune. The first one is number of tasks. You want to use a lot of tasks to generate enough loads for your metadata server, for your MDS server. So if you have less than 100 tasks, you won't see a better performance number. And the second one is number of files. So if you use like tens of thousands files, most of the operations are done in memory. There won't be any disk IOs before the task finish. So you want to like about 1 million files or 100,000 files to eliminate the caching effect. And then the third thing is you want to run MD test in multiple iterations, 3, 5, 10 times, because we see fluctuations. So you want to use multiple iterations and get an average out of it to eliminate the factors of outliers. And then the next one is if you have a lot of physical nodes, that won't be an issue. But sometimes you have limited number of client nodes and you want to run a lot of tasks. So you want to use the unique mount option so that each task will have its own mount points. That will eliminate the limitation of that RPC log, which will serialize all the metadata modifications from a single client. So basically, it just simulate a lot of clients using a single physical client node. The next ones worth mentioning is the -A and -O options of MD test. Both of them will exclude OSTs from the test runs. So -A will use make node to create new files, and -O will create zero striping files. Both of the things will not involve OSTs in the file creations. But -O will have one more RPCs than -A, so we'll see a better number with -A. The last one is direct structures. If you want to try the single shared directory, or you want to use distinct directories for each tasks. So the latter one will get better results. Also, there are some other parameters you can use to manipulate the tree that MD test is going to generate. The fan out, the depth. So next thing about methodology is how you design your tasks. Normally what we do is you either fix the number of client nodes and you vary the number of tasks per client, or you fix number of tasks and you vary the number of client nodes. In either case, you want to see an increased performance with the increased number of tasks. And then while you're running the test, you run some monitoring or profiling tools in the background to gather the stats. So if there's anything happen, you have some data to interpret the results. And the next thing is kind of straightforward, is that if you want to evaluate a lot of factors, you change one at a time, and then you compare the difference and give a possible explanations. Then also you want to test the cases with like non-empty file systems, or defragmented file systems, or file systems, or the case that the backend storage is doing the rebuild, and all those situations. Okay, so that's about the methodology, and I'll talk about how to investigate metadata performance issues. A couple of issue types. The first is that you see performance degradations between different versions of Lusters, either client, server, or both. And another type of issues is that you expect certain performance numbers from your specific hardware configurations, but you fail to see the results, and you want to know why. And the third thing is that your end user complains. LS commands take a long time to return. I see some sluggish response. So the methods for diagnosis is that the most effective one is profiling the system while the things is happening. Also, you can utilize the Lustre stats, see if there's any abnormal situations on the server. Or you have to generate a crash dump from the server to see if there's any deadlock or lockup. For profiling tools, if you want to see the load of your backend storage, we normally use IOStat, see if it's overloaded. And then the perf and O profile is used for CPU load. You want to see if there's any kernel threads hogging the CPUs and start other kernel threads servicing the requests. But most of the time, you want to understand the latencies, why some operations take longer to finish. So we first tried latency top, which will give you a list of the call traces of the top 10 or 15 call traces that have the most latency in the system. But the limitation is that it can only trace the user space applications. It cannot trace kernel threads. And also, it only gives you the top 10 of all those call traces. So we move on to systemtap. Yesterday, some talks about the presentation done by Jason Rapoi. So we follow his example to use systemtap to profile Lustre on the metadata performance side. Here is talk about the Lustre stats. There are already a lot of presentations talking about how to monitor Lustre stats, and here it shows is the cluster store manager of Xyratex. It shows the dashboard and the performance tabs. So all of this is that visualization of the Lustre stats will help a lot for administrators to quickly spot any abnormal situations on the server. And the last we'll talk about a case study recently that happened on the metadata performance issue. So the problem is that metadata performance degradation was observed in Lustre 2.3 clients compared with 1.8 and 8 clients. And the benchmarking basically just create a bunch of tasks, and then those tasks will create files under a shared flat directories and then delete it. The creation is about the same between 2.3 and 1.8 clients, but we see the deletion rate of 2.3 client is just a third of 1.8 clients. So first thing we try is to replicate it, and lucky enough we replicated in our own lab, and then we use systemtap to profile the latencies of the unlink call stacks. And to the right is a example script. It's very simple. It just calculates the delta spent in each of the functions, and at the end it will generate a histogram of the latencies by time slot. And here shows the example of the latency of LL unlink functions. On the left is the one for 1.8 clients, and on the right is 2.3 clients. So the task will create 64,000 files using 8 clients. So each client will create 8,000 files and delete them. So for 1.8 client, you'll see almost all the unlink operations happened within 2 milliseconds. But for 2.3, we see a lot of unlink operations spend more time than that. So we keep drilling down along the call stacks, and we see most of the latency comes from clients just waiting for response from the MDS. So we went on to the server side and profiling the unlinked code path. This is simplified code for the unlink on MDT. So basically it locks the parents, and then it will do the extra on disk change in MDT unlink. And the profiling result shows that the extra on disk latency is about the same. But for 2.3, it spent a lot more time trying to log the parents. So we need to answer why the 2.3 clients make the server waiting a lot longer, requiring the log on the parents. So we inspect the code of the benchmark applications, and we found out that the workflow is like this. For file creations, each task will get a segment from a dictionary to use the words generate the file names and then just create it. But for file unlink, each task will use reader to get the next dir entry, stat the dir entry, make sure it's a regular file, and then delete it. So basically, all the clients will do a lot of readers before doing the actual deletions. And we found out that there is a big difference between 1.8 and 2.3 in terms of reader, is that the reader trunk size get increased from single page to 1 megabytes. And the bigger trunk size will make it's more possible to get log conflicts among the clients, and you get more log consolations and log ping pongs. That will make the unlink take longer on server. So the lesson learned from this performance issue is that certain workflows in benchmarking tools or user applications may not be able to achieve the optimal metadata performance that Lustre can offer. So there are spaces for optimizations. And the second thing we learned is that systemtap is proved to be an effective tool for latency profiling and performance diagnosis. So that concludes my presentations. Thank you.
So I see you have mentioned MD test and other such test tools. You probably do realize those poorly express the actual metadata workloads that are being executed by applications, unlike I/O benchmarks that are actually doing I/O in a way
Right.
very similar to how actual applications do it.
Right.
You barely see any real applications that open and close files with very little operations in between, with little succession. And while it might be a somewhat valid way of estimating workload from a much larger cluster, it still is no match for what actually happens, which is like you have a large cluster, everybody does an open at once, and then they actually do tons of other stuff before they actually close. And what you measure with MD test is open plus close latency, and that's it. So
Right.
very far away from what actually happens. Oak Ridge actually did a lot of interesting work in this area. Dave Dilo created a tool called DeerBench that runs a whole cluster that basically just does the open and times just that. And I think it's much more valid approach.
Okay. Thanks.
So have you tested all flash arrays for metadata operations?
I'm sorry, test what?
All flash, like SSD arrays?
No, we didn't test the SSD as the backend. Yeah.
So do you expect any improvement?
You might get some, that's my guess, you might get some performance benefits if you use SSD as a journal device, maybe.
Actually, and that's me again. I think your expression of how journal operates is a little bit incorrect in a way that journal actually gets mostly sequential I/O, and so you can get by with a relatively slow journal device. But what really kills you is when the journal is overflown, then you cannot create any more transactions until you flush the journal
Right.
content back into the file system. And that's where lots of very random I/O comes from.
Right.
So by having kind of a flash journal, you don't gain much. But if you actually have flash on your main data device for MDS, I would expect that would be very beneficial. I don't know if you have actually tried any of that.
No, we haven't. But yeah, it's a good point.